Let's understand sinusoidal and exponential signals. First of all, we'll understand continuous time signals and then discrete time signals in the next lesson. So, in a continuous time signal, we generally express a continuous time signal like this, and exponential signal like this, c into e to the power at. Okay, this is exponential, where c and a, these are complex numbers. These are complex. So this is what we will understand. For the time being, what we'll do, we'll see different scenarios, like when c and a are real numbers, when a is imaginary, and so on. And then finally what we'll do, we'll encapsulate all of them and then we'll analyze when both c and a are complex. Clear? So this is our basic continuous time signal in exponential form. Let's see the first topic. That is when we have real exponential signal or function. That is, in this xt, c is a constant, and a is a constant. Now both of these variables are actually constants. So what? So we have three. So in this case, we'll have case 1 when a is greater than 0. What if a is greater than 0? Then this is a constant, this is exponential function. In this case, our signal will be like this. In this case, our signal will be like this. See, exponentially rising. This is xt, this is t. Okay, so when a is greater than 0, our signal will be like this, exponentially rising. This will be at t equal to 0. See, this will be equal to c. Okay, this is the first case. Second case is when a is less than 0. Our second case is when a is less than 0. Then what? See, when a is less than 0, then this c e to the power minus at, it will be like something minus bt. Let's say it is minus b. Then it will be exponentially decreasing. That is, like here we have this signal and then it will decrease. So this is the second case. And at t equal to 0, this will be c. Okay. So when a is less than 0, our signal will be exponentially decreasing. And when a is equal to 0, then what? When case 3, when a is equal to 0. See, when a is equal to 0, this will be 1. So our signal will be like this. It will be a constant. Clear? So this will be equal to c. So at a equal to 0, it is simply c. Okay. Second case, we'll see when our exponential signal is basically periodic complex. Periodic complex continuous time signal. It is called periodic complex continuous time signal. CT means continuous time. So what we do, we express it like this. xt is equal to e to the power j omega 0 t. So here what we do, for convenience we take c equal to 1 for convenience only, and this a is purely imaginary. Okay, so let's understand this signal. Now we are saying this is a periodic signal. Let the time period be t. Then we know this will mean if time period is t, then this means this is j omega 0 t plus t. So it will repeat after t. This is the meaning. Or this can be expressed as j omega 0 t into a e to the power j omega 0 t. Now this is possible only when this is equal to 1. Clear? Again, we are talking of periodic signal. So periodic means if the time period is t, this will be equal to this. It will repeat after time period t. So this can be expanded like this. This is possible only this and this when this is equal to 1. So in the case of periodic signals, we'll have this equal to 1. This, and when is this possible? It is possible only when when omega 0 is not equal to 0, then this will be 1 only. I'm rubbing this so that we are able to write in detail. So ej omega 0 t equal to 1 means we have two cases. First case is omega 0 equal to 0, and second case is when omega 0 is not equal to 0. When this is not equal to 0, then this equation will hold when t will be equal to 2 pi by omega 0. And if this is okay, this is only possible only when this is equal to this. Why? Because when we have this particular value of t, this will mean ej 2 pi. This is cos 2 pi by Euler's equation, cos 2 pi plus j sin 2 pi. So this is 1, this is 0. So for t equal to 2 pi by omega 0, this equation holds true. This is called time period. Okay, and the lowest time period will be the omega, and corresponding to the lowest time period will have fundamental frequency omega 0. What about this? When this is equal to 0, our signal will be periodic undoubtedly, but fundamental frequency will not be defined. That is, fundamental frequency is undefined here, and fundamental frequency is omega 0 here. Omega 0, that is 2 pi f0 frequency. Okay, so this is the case, and you can observe that e to the power j omega 0 t and e to the power minus j omega 0 t both will have same fundamental frequency. So this should be kept in mind. Now let's see sinusoidal signal. How do we represent it? Sinusoidal signal. How we represent it? We represent it like this: xt is equal to a cos omega t plus phi, where a is the amplitude, omega is the angular frequency in radians per second, phi is the phase difference in radians. Okay, and if you plot signal, it will be like this. This corresponds to phi in radians when this is in omega. Okay, and this will cut at a cos phi. This is the signal. You know this. You have seen this signal. It can also be expressed in exponential form. This can also be expressed like this: a by 2 e to the power j phi e to the power j omega t plus j a by 2 e to the power minus j phi e to the power minus j omega t. So if you expand these exponential terms, you will get this. Clear? So at omega equal to 0, what you have? The fundamental frequency is undefined. Frequency that we define as 1 by f, which is 2 pi by omega. For fundamental case, we write like this. So for omega equal to 0, your fundamental frequency will not be defined. The rate of oscillation will be 0. So this is how we express sinusoidal signals. Now let's understand what is the energy and power in exponential and sinusoidal signals. So what we do? Energy in a time period 0 to, let's say, t. What is how we calculate energy? Yeah, you know this. Okay, and you have seen for one time period this is equal to 1. That is, this is what you will get. You will get t. If you write it like this, you will get 0 to t. So you will get t. That is energy in one cycle. This energy in one cycle is equal to t. So energy in infinite number of cycles will be infinity. Clear? Now second thing, this is your energy. Now let's talk of power. Power is energy, average power. We write it like this: average power is what? Energy in one time period by the time period. So this will be t by t, that is 1. So energy is 1. Also you can see it like this: limit t tending to infinity 1 by 2t minus t to t e j omega 0 t square dt, from the basic definition. Now again, this is 1, this will be 2t, so 2t by 2t 1. So what you will get is 1. So average power is 1, and when we are talking of average power, it is 1. If you have 10 cycles, then 10 1 plus 1 plus 1 10 by 10, so 1. So average power is 1, while the energy of the whole signal is infinity, while it is t for 1 cycle only. Okay. Now let's understand harmonically related signals. What is the meaning of harmonically related signals? Signals which have same fundamental angular frequency. We saw this 2 pi by omega 0. Also, this is true for this. If you have multiples of 2 pi, then also you'll have equal to 1. This function which we had done there, equal to 1. So if this will be k of, not this one, if we write the fundamental angular frequency be omega 0, then multiples of this will also satisfy this equation. So signals which have frequencies that are multiples of the fundamental angular frequency are called harmonically related signals. Okay, k is what? K is 0, plus minus 1, plus minus 2, and so on. So now we can analyze, we have seen different components, we can analyze the general complex exponential signal. I had written xt is equal to c e to the power at, where c and a are complex. Let's define c as this, e to the power j theta, okay, and a be r plus j omega 0. So both these numbers are complex. Then what? We can write this signal xt as this, e to the power j theta, okay, so this into e to the power at, this is e to the power r plus j omega 0. So we can write it like this, or we can write like this, c e to the power r into, we forgot t, rt, we can take it out, rt, and then we'll have e to the power j omega 0 t plus theta. Okay, so we can write it like this, or further it can be expanded to like this, e to the power rt, first term will be cos omega 0 t plus theta. This is in exponential form and this is in sinusoidal form, j sine omega 0 t plus theta. Okay, so this signal can be expanded to this signal. What is the meaning? I am rubbing up to this and we'll see the signals. I'm keeping this final signal. So what is the meaning of this? See, if r case 1 when r is equal to case 1 when r is equal to 0. When r is equal to 0, this will be a constant. So real part and imaginary part both will be sinusoidal waves. So this is simple sinusoidal waves, one in direction and one 90 degrees to it. So this is a sinusoidal wave when r is equal to 0. Now case 2, when r is greater than 0, when r is positive. Now you see, this is sinusoidal, this is positive, so, and this is exponentially increasing. So the graph that we'll get will be like this. See, this is a sinusoidal wave which is the amplitude of which is rising exponentially. Okay, so this c e to the power rt plus minus c e to the power rt, this acts as an envelope inside which this sinusoidal wave passes. Okay, so this is when r is greater than 0. Case 3, when r is less than 0. What we'll get when our r is less than 0? Now see, when this is less than 0, we'll have sinusoidal signal that is under an envelope that is exponentially decreasing. There it was increasing, here this is decreasing. So we'll have like this. This will be the envelope and our signal will be like this, sinusoidally, a sinusoid which is exponentially decreasing. Clear? This is your xt and this is your t. So this is when both c and a are complex. So we have analyzed many signals. In the next lesson, we'll see this same analysis for discrete signals. Okay, and then we'll enter into systems, linear time invariant systems.